Hello everyone, my name is Akhil. We are having weekly sessions of the Basics of Material Engineering course where we solve the problems before the assignment, similar problems. Okay, so today's topic is on phase diagrams. So here we were actually given a phase diagram. Now our job is to find the different phases and the reaction points. So this is corresponds to cobalt and tungsten. Okay. So let's begin finding out the different phases that are available. So if you see the phase diagram, initial top most usually will always be completely molten state. So that would be liquid. Okay. And you should next look at the extremities. So on the left side here there is one small region. So this we can denote as alpha, this left extreme. And then right side also we similarly have an extreme. So this is beta phase. Okay. So these are the two alpha phase and beta phase, solid solutional phases. Now we need to identify the other phases. So here if you see the liquid turns into some kind of after solidifying a solid solution. So that would be beta, or we are already given beta. So this we can take as gamma. And we have here interalloy phases or intermetallic phases. So this one we can denote as delta, and we here we epsilon. Okay. So first we can identify the initial phases like this. First extremities, and then in the middle. So when liquid to solidifying, there will be phases, solid solution phases starting, and then these are the at only specific combinations you have special phases that exist. Okay. Now this would be on the left you have pure alpha, and on the left you have pure delta. So this would be alpha plus delta, and then here you have on the left gamma, and then on the right delta. So this would be gamma plus delta phase. So this would be alpha plus gamma phase similarly. Okay. Now this would be delta plus epsilon phase. Now this would be epsilon plus beta phase, and this would be liquid plus beta. Okay. So the melting point of W is actually very high, and that is out of the graph. So that's why we have these dotted lines. Next, here we have this gamma plus epsilon. On the left we have gamma, and on the right we have epsilon. And here we have liquid plus epsilon. Okay. And this would be liquid plus gamma, and then this would be liquid plus gamma. Okay. So this is how we can first identify all the phases everywhere. Next we have to identify the reaction points. Okay. So first let's look at this point. So here we have liquid plus solid converting to a single solid. So what would be that type of reaction? So in general the main reactions are, if we have liquid upon heating converting to two types of solids, then we have eutectic, and eutectoid would be solid converting to two types of solids. Okay. And then peritectic would be liquid plus solid converting to new type of solid, and peritectoid would be two solids converting to some new type of solid. Okay. So now we need to identify these points in this phase diagram. So here we have liquid plus solid converting to new type of solid. So this is a peritectic point. Okay. Next. Here, if you see, we have liquid converting to two types of solids. Okay, so peritectic, here we have liquid plus beta converting to epsilon, and then here eutectic, liquid converting to two solids. So gamma plus epsilon. And what else? Here we have one more point where two solids gamma plus epsilon converting to delta. Okay, gamma plus epsilon converting to delta plus. So this is peritectoid. So what other points we have? So if you see here we have one more point. So a single solid is converting to two solids. So this is eutectoid reaction. So gamma is converting to alpha plus delta. So eutectoid. Okay. So this is how in the phase diagram first you can identify all the phases and then you can identify the points. Okay. Any doubts in this? Okay. So let's move on to the next question. So in the same phase diagram, cobalt and tungsten phase diagram, now we need to identify the phase compositions and then cobalt and weight for each phase for points A and B. So here we are given point A and point B here. Now we need to identify what are the phase compositions. Okay. So first let's look at A. So to identify the phases actually what are the each at each point for a given temperature and composition the fraction of each phase, first you need to draw a horizontal line and find the points where it intersects with any of the phases, pure phases. Okay, so now this point this is 10, so take it as 7 and then this would be 44. Okay. Now at point A we actually have gamma phase and delta phase, right? So at point A we have gamma and delta phases. Now what will be the fraction of gamma phase? So fraction okay. Let's do it this way. Fraction of gamma phase. Now the composition at for, so here we'll use the lever rule. So it will be proportional to this length for the gamma phase. So because we want gamma, you need to actually take C delta minus Ca by C delta minus C gamma. Okay. So this is how we will get at A the composition of alpha gamma phase. So here we have delta as 44 minus Ca 25 by 44 minus 7. Okay. So if we calculate that, 44 minus 25, 19 by 44 minus 7, that is okay. So 51.3%. So at point A, we have gamma phase of 51.3% and delta phase of 48.7. Okay. So this is basically lever rule, and this is how we can identify at each point the composition of the phases or the fraction of each phase. Okay. Now we need to do similar thing at point B. So at point B, what are the two phases that are available? At point B. So again draw two horizontal line. So that is intersecting epsilon phase and beta phase. Okay. We have epsilon phase and beta phase. Now what would be the epsilon phase mass fraction? Horizontal line, that's it. At a given point, we are just drawing an horizontal line. I am not sure what tie line means. I haven't heard. So now we want the phase of W epsilon, fraction of epsilon. So similarly, using the lever rule, uh, so composition at beta minus composition at B by composition at beta minus composition at epsilon. Okay. So this would be composition at beta is 99.7 given. So 99.7 minus composition at B is 85 and 99.7 minus composition at epsilon is 75. Okay. So this will give us the fraction of epsilon phase at point B. So let's do the calculation. 14.7 by 24.7. Is that correct? 15.7 by 24.7. Okay. So it's almost 59.5%. Okay. So Suresh, we have also discussed from their graph how you can identify the phases and all. So I think you can check the video later to get that. So this is how you can get using lever principle the compositions. Now we need to also find out at point A and B what are the compositions in each phase. Okay. So that means, yeah. So that is basically at point A you have gamma and delta phase, right? So what is the composition of gamma phase and what is the composition of delta phase? So that is same as what are the horizontal lines which we have drawn, the intersecting points. Okay. So that we have already estimated. See, the delta phase has a composition of 44% and the gamma phase has a composition of 7%. Okay. So using that only we actually estimated the fraction of gamma phase in the total phase. Okay. So let's move on to the next question. Yeah. So here we are given some hypothetical phase diagram. Now the question is, upon complete solidification of binary alloy system AB, the fraction of pro-eutectic alpha phase is 0.5. The alloy composition in terms of weight percent of B is. So at some composition of B, the cooling resulted in pro-eutectic alpha phase of 0.5 fraction. Okay. So what exactly is pro-eutectic phase? So this pro-eutectic also means primary eutectic. So it's basically even before the mixture formed, there will be some alpha present. So whatever that alpha in the solid form is the pro-eutectic alpha. So when you are solidifying uh, from complete liquid state, let's say from here. So from this point, the crystallization starts and you have some amount of alpha. And at this point, you have some more alpha. Now, as you go just a little bit down, all the liquid converts into solid. So all the liquid converts into actually eutectic mixture of alpha and beta. So at this point, you have some alpha which is already solidified, and the rest of the liquid forms a eutectic mixture of alpha and beta. So the original alpha which was present is the pro-eutectic alpha. Okay. So that will happen only in this case. Let's say if you are actually doing here, the entire liquid converts into pure alpha phase, solid solution alpha phase. Only in this case, from here to here, you will have a pro-eutectic alpha and an eutectic mixture of alpha plus beta. So this point will actually have pro-eutectic alpha plus eutectic mix of alpha comma beta. Okay. So at this point, basically liquid turns to alpha plus beta. So this is the eutectic point, and alpha plus beta is the eutectic mixture. Okay. Now it's given that proeutectic alpha phase present is 0.5 of the total fraction. Okay. So if you have to find the proeutectic alpha's phase, basically if you consider a point here just above the eutectic line, so at that point you have some alpha and some liquid, right? Let's call it G. At G, you have a mix of alpha comma L. So what we are saying is, if you just cross the eutectic point, it will form a proeutectic mixture of alpha and eutectic mixture of alpha plus beta. These are above T eutectic. This is below T eutectic. Okay. Now it is given this is 50% of the total thing. So that actually means just above the eutectic line, the liquid should be 50%. The alpha should be 50% and the rest of the liquid should also be 50%, right? Because it's given proeutectic alpha phase is 50.5 of the total thing. So that means if it is 0.5 exactly, you are exactly at the midline. Or if you write W alpha, which is above eutectic line. So this would be Cl minus C alpha by Cl minus Cl minus some point Cx, or let's Cg, right? Let's Cg minus Cl minus C alpha. Okay. So this is given as 0.5 already. Now we have to find what is this composition Cg such that you will get a proeutectic mixture of 50%. So Cl is 61.9, Cg we don't know, and 61.9 plus C alpha is 18.3 is equal to 0.5. So Cg is equal to 61.9 minus 0.5 of 1.9 minus 18.3. Okay, this you can just write 61.9 by 2 plus 18.3 by 2. So this would give how much? 61.9 plus 18.3 divided by 40.1%. So is this clear? So if your actual composition is 40%, then when you are cooling down from full liquid, you will have some primary alpha liquid and then proeutectic alpha and then eutectic mixture of alpha plus beta. Okay. Is this clear? Yeah. So next question. So here we have a single component system. The maximum number of phases that can coexist in equilibrium is. So do you know the answer, Suresh? You know for water triple point? Yeah. So how many phases at a point can water have at max? Yeah. So that is the actual answer here. So the way you can find that is, so you know the degrees of freedom is related to, so number of phases at that at a given point, and number of independent non-composition variables like temperature and pressure, and this is the composition components, number of components. Okay. Number of non-component variables like temperature and pressure. So this pressure will come only in gases or liquids when we are considering, because when we are taking metal alloys, the pressure doesn't matter, because we do everything at atmospheric pressure. Okay. Please remember that also. Now the lowest possible degrees of freedom is 0, right? Okay. So if we take 0 and number of components is a single component, and temperature and pressure could be two variables, and then we need to the number of phases. So P is equal to 3. Okay. So the best example is water for this case at the triple point. Okay. Yeah. Next we have one more question. We have an AB alloy with composition 55 weight% B and 45 weight% A. Okay. And alpha and beta phases already given 50% each. And then beta phase composition is 90 weight% of B. Now what is the alpha phase composition? So that is the question. So can we answer this? So we have beta phase and we have alpha phase U, and we have alpha plus beta mixture, and beta phase composition is 90 weight% B, and alpha weight percentage we don't know, so let's call it X. That's what we are supposed to find, and the actual composition is already given as 55. Okay. And then alpha and beta are given as 50% each, so that means this two lines are equal. So basically what this point has alpha and beta, and the alpha and beta are equal, and beta has 90 weight% B. So how much weight% should alpha have so that the composition would be 55? So that is the question. So for this the simple formula is, at any given point the actual composition here it's already given as 50%. No. So let's say if nothing is given, this also, let's say some okay, some A. Okay. At composition Ca. Okay. Yeah. W alpha, some fraction W alpha. Now you have W alpha, like fraction of alpha W, and then fraction of beta as 1 minus W alpha. Now beta can have only 90% B. Okay. And alpha will have some X% B. Okay. Now the total composition, what would it be when you have both? So correspondingly their fractional proportionality, right? So W alpha into X plus W beta into uh, C beta. Okay, this should be whatever percentage we are already given, composition C. So this composition, okay, this is C beta and this is C alpha. You understood how I wrote this? You have a total final composition, and for that you have two individual components, alpha and beta. But alpha can have only C alpha composition and beta can only have C beta composition. And you have beta as a fraction of W beta and alpha as a fraction of W alpha. Okay. Yeah. So let's say if both are equal, then the average composition should be the total final composition, right? You understood my point? You have alpha, you have beta, and let's say you have both of them equal. Then what would be the final actual composition? Let's say this has 10% and this has 90%. Ah, what would be the alpha plus betas in that? What would be the composition? It's just the average, right? Yeah. So, but here it's some fractional W alpha and fractional W beta and composition C alpha and composition C beta. So we are just multiplying the individually and then that should be the total composition. So here we need to find W alpha. C alpha is 0.5 and W beta is 90 and C beta is also 0.5. Its total is 55. So W alpha you can write 0.5, 0.5, right? I am multiplying everything with 2. So 110 minus 90. So 20. So if and only if you have this point as 20 weight%, then a equal mixture of alpha and beta phase will give you 55 weight% total. Yeah. So I hope this is clear. Now one new question. Uh, in a binary phase diagram, the degree of freedom at eutectic point. So what is the eutectic point? Liquid turning into two solids, right? So this is cooling, this is heating, cooling, cooling, cooling. Yeah. Now at this point, what is the degrees of freedom? So the degrees of freedom, we know that it is equal to C plus N minus P. So how many phases are there at this eutectic point? 3. So because in the metal alloy we don't consider the pressure, so there is only temperature. So N is 1, non-composition variables. Yes, but two solid phases, right? One liquid converts to two solids, alpha plus beta. So this point, liquid connecting to two solid phases, alpha plus beta. So this is the eutectic mixture. So if liquid is forming single solid, then it's just a solidifying, right? It's not forming any phases. Pure metal case similar to if it's forming a single solid. Okay. Now components binary phase diagram. So two components. So what would be the degrees of freedom? 0. Is this clear? Yeah. So think of it like this. Take eutectic point only. So this is liquid. This is alpha plus beta. This is liquid plus alpha. This is liquid plus beta. Okay. Now eutectic point is basically this point, right? So degrees of freedom basically means what are all the variables that you can change. Variables like composition, temperature. In the phase diagrams, we don't consider pressure. So yeah, what can we change so that we still be at the same phase, same like phase mixture. So this has both the liquid and alpha and beta. You have to be at exactly that point. What are the variables that you can change to be at that point? That is basically the degrees of freedom. So we can't change anything, right? If you change anything, you are, let's say if you are changing temperature, then you go to this point or this point, right? So it's not a eutectic point anymore. Let's say you are changing composition, then you go to these 2 points. Again, you are not maintaining the eutectic exact point. Okay. So the degrees of freedom is 0. Yes, yes, exactly. So in triple point, let's say, okay, I don't remember. Okay, let's some random triple point. This is not exact. Let's say this is how it is. This is pressure and this is temperature. Let's say this is not a real graph, so don't take it. Now, let's say if you are at this triple point. Now, let's say if you are changing composition or pressure or temperature, you won't be again at that point, right? So degrees of freedom would be 0. But let's say you are at this point. You are here. Now you can change temperature and pressure so that you can still be on this line, right, Suresh? So you will still have gas and liquid at an equilibrium, but you can keep on changing the temperature and pressure such that you are on this line. Okay. So this line is basically degree of freedom 1, because the temperature and pressure you need to change together. If you change only temperature, keeping the pressure constant, you are out of the phase. So that is not a, so degrees of freedom are not 2. Okay. Yeah. So this way you can, oh, okay. So this is liquid, huh? Okay, okay. This, huh? Oh, okay. So yeah. Now is this clear? The degrees of freedom? Yeah. Yes. So let's move on to the next question. This one. Because binary phase diagram, right? Binary, so number of components are 2. Yeah. So now, so we are given copper CuAg phase diagram. Now maximum solubility of Ag in Cu. So can you tell me the answer? Maximum solubility of Ag in Cu. Yeah, see, the maximum solubility points are simple. These are basically the extreme points. So this is actually the melting points, right? These are melting points, and these are pure phases. Now let's say you are slowly increasing from the 0 phase Ag. How much you can have a proper solid solution? So this is the maximum point, right? If you go more than this, so you are actually forming 2 phases. In this case, you are forming alpha plus beta phase. Here you are forming alpha plus liquid. It's not a single solid solution. Okay. So this is the maximum solubility. That's it. As simple as that. Okay. So basically solubility in this case is it should form a proper solid solution. So there should only be single phase. So what is the maximum composition of silver where a single composition exists? That's it. So that is this point here. So it's already mentioned here, 8. That points are mentioned. Now maximum solubility of Cu in Ag. So in pure Ag, how much maximum you can see copper you can put? So can you tell the answer for this? Maximum solubility of copper in silver. So previously we did maximum solubility of silver in copper. Now it's the reverse. We have actually silver as the solvent, and what is the maximum copper that you can have? Yeah, this point. So but this is in composition Ag, right? So you have to do 100 minus 91.2%. So it's 8.8. So this is clear. So this point. So you can maximum add 8.8 percentage of copper to silver to form a solid solution, and 8% of silver to copper to form a solid solution. If you add anything more, you will form a phase mixtures. Okay. Yeah. Now next question. We have 58% Ag and temperature just below eutectic. Relative fraction of alpha phase. So this case 58% of Ag. So this line, and then temperature just below the eutectic. So in this, what is the eutectic point, Suresh? Yes, exactly. So this is the eutectic point. A single liquid forms two solids. So liquid forming alpha plus beta. So this is eutectic point. Now just below the eutectic point, what will be the relative fraction of alpha phase? So basically at this point. Okay. So we need to find the alpha phase. So relative fraction of alpha phase. Yes. No, 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 no. Eutectic point will always be one point only. Yeah. So this alpha plus beta is a mixture of two phases, alpha and beta. Okay. Yeah. Now we have this inside at 58%, just below the eutectic point. What will be the relative fraction of alpha? Okay. Pure total alpha phase. Now to get that just below the eutectic point, what are the phases we have? At this point, what are the two phases which we have? Just below the eutectic point. So you can just look at the eutectic point. So what are the two phases which we have? Yeah, yeah, just below. So we only have alpha and beta. That's because there is no liquid below the eutectic point. So we have alpha phase and beta phase. And what is the relative fraction of alpha phase? So W alpha. So if you know the lever formula, what should we do now? Whatever that point, let's denote it as P. Is this correct? So it's proportional to this length. Basically, this lever principle is basically like this. Let's say you are here. What do you expect? Which phase to be more? Alpha phase to be more, right? Because you are very close to the alpha phase. No, no, it is that way only. it should be uh, uh, like alpha phase should be more, but we are actually doing with the lengths. So which length is more, this length or this length? Okay, okay. So let's say we are here, and let's take P1, P2, P3. Okay. P2 is, yes. So, but the beta phase length is more, right? Yes. So it's far away from the beta phase. So beta percentage should be less. But when you are doing the proportionality here lengths, uh, so weight fraction of alpha is proportional to the length between point and the beta phase point. Yeah. So simple. So C beta minus Cp by C beta minus C alpha. That's it. So for this point, C beta minus Cp, because we want composition of alpha at this point. So C beta minus Cp, this length divided by this length. Okay. So opposite, as you first said, we need to take the opposite. So C beta is 91.2, Cp is 50 by and 8%, right? Yeah. So this would be the total fraction of alpha phase. Okay. So 49.52%. Okay. So just below the eutectic point, you will have alpha phase of 49.52 and rest would be beta phase. Now the next question, for the same 58% Ag point and temperature above eutectic, what will be the relative fraction of alpha phase again? So now we are here, just above the eutectic point. Okay. Now what are the two phases at this point? Yes. So we are above the eutectic point. So at this point there will be alpha and liquid. Okay. So now alpha comma liquid. Similarly, fraction of alpha would be Cl minus C. Here we are giving Q by Cl minus C alpha. Is this okay? So alpha's composition at this point would be proportional to this length, right? Yes. So 71.9 minus 50 by 71.9 minus 8. 21.9 by 63.9. So 34.27%. Okay. So here we will have alpha was 34.27% weight fraction, and here we will have alpha of 49.52%. So now can you tell me, just by crossing the eutectic point, the alpha percentage is increasing by so much from 34.27 to 49.52. Where do you think that is coming from? Suresh? Yeah. So what? Yeah. So yeah, not a problem. So when we are going from Q to P, okay, at Q we have alpha plus liquid, at P we have alpha and beta, right? So when you are going from Q to P, alpha at Q is 34.27% and at P it is 49.52%. that converts to eutectic mixture of alpha and beta, right? Yeah. So from the liquid, that extra alpha is coming. So that I wanted to like to identify. That's why I asked that question. Okay. Now, next question is at 78%. So here there is one very important thing which we discussed in the earlier question. Yeah. So whatever alpha which is already there, even before complete cooling, that alpha is actually called primary alpha phase. Okay. So in the 49.52 percentage of alpha in the point P, 34.27% would be primary alpha. The rest would be eutectic mixture of alpha, like the alpha in the eutectic mixture. So at this point, you will actually have alpha and alpha plus beta. This is pre-eutectic alpha or primary alpha. Okay, pro-eutectic, right? And this is eutectic mixture alpha and eutectic mix beta. Okay. Yeah. Now the next question is 78% Ag cooling down from 1800 degrees slowly gives rise to a mixture of. So at 78%. Okay. So this diagram has become very congested. Let me. Okay, the question is at 78% Ag, we are cooling down from 1800. What will be the phases in the cooled phase? So at 70, this case. So here, what will we have at this point anyway? So what will be the phases which you think should be there at this point in terms of pro-eutectic alpha and alpha beta eutectic mixture in that sense? Eutectic mix of alpha and you are on the left side actually. So you are on this side. So what will be there mainly? Yeah. So primary alpha a little bit, right, because this length is so small. Yeah, a small amount of primary alpha, a small fraction of primary alpha and large fraction of eutectic mixture. Yeah, that is in eutectic mixture, no, eutectic mixture of alpha and beta. So when we say eutectic mixture, both are there, right? Yeah. So, but when you, if you are to the right, then whatever you are saying, you will have primary beta and then eutectic mix of alpha and beta. Okay. Yeah. So next question, the composition of alpha, proeutectic alpha, eutectic alpha and beta. So previously whatever we have already discussed. So the question is at point P, how much would be primary alpha and how much would be actual alpha in the eutectic mix? Can you tell me the answer? So did you understand the question? Okay. Read the question once. I'll wait. Yeah, yeah. So at 40% and then just below tectic point. So this point, right? Uh, Now the question is how much the would be proeutectic alpha, eutectic alpha and beta. Yeah. So can you tell me how we can get this? Yeah. So proeutectic alpha is basically the alpha before the solidification, right? So whatever alpha which you will get here at Q, like in the previous case, that would be proetic alpha would be W at Q W alpha. Okay. So this we have already solved as at Q we got a percentage of alpha as 34.27%. Okay. So this much is already solidified to alpha. Okay. Now when you cool even more, the liquid, the rest of the liquid, basically liquid would be so 65.73. Yeah. So this much amount of liquid now will form a eutectic mixture of alpha and beta, right? Yeah. So now from this 65.73%, some will be alpha, some will become beta. So here we are asking in that how much is alpha? What is that alpha? Eutectic alpha, and rest is beta. So at P we already got W alpha, like total alpha. So this is pro-eutectic alpha plus eutectic alpha. Okay. So we already did from the below the calculations, right? We got around 14.52%. Okay. So now we know pro-eutectic alpha is 34.27%. So what would be the eutectic alpha? So 49.52 minus 34.27. Is that correct? So 15.25%. So basically what I'm saying is think of it like three phases. Okay. Below the eutectic point somewhere here we have primary alpha, P alpha I am denoting, eutectic mixture alpha, eutectic mixture beta. Okay. Okay. Now total alpha you got as 54.27 percentage, right? When we did that earlier calculations. Yeah. Now if you are just above, there you got W alpha, which is actually primary alpha, right? Alpha which already formed, that is basically primary alpha. You got that point? 49.52. And this is 34.2. So the alpha which is already formed is the primary alpha or proeutectic alpha, and the alpha which forms new is the eutectic alpha. Basically, it's a eutectic mixture of alpha and beta, that alpha. And then we have the rest as beta. So now we know primary alpha and we know total alpha. What will be eutectic alpha? The difference only, right? Yeah. So that's what we did. That's it. Okay. Okay. Yeah. So that is it for today. So basically today we have covered what will be the different eutectic, eutectoid, peritectic, peritectoid points, and then yes, yes, yes. So yeah, tectic. Oh, I actually uploaded. See, basically the Google these documents would be in that Google folder. Okay. Even if I don't paste the link in that Excel sheet, it will be there.